Today, the drawing board by TBPi presents the shape of molecules. So here's a basic roadmap of what we'll be looking at. So first, we can look at the Lewis structure of different atoms, seeing how the electrons are either on atoms or shared in between atoms and molecules. Then we can look more specifically at those electron pairs. Then we can see how those electrons impact the geometry of the molecule using what's called VSEPR theory. Then we can go on to predict more specifically what bond angles we'll see in that geometry. And then we'll end with looking at the polarity of molecules, whether they are polar or non-polar. So we'll start by looking at Lewis structures of different atoms. So a Lewis structure is basically visualizing the electrons on atom by just drawing dots for each of them. On the periodic table, for each of these different columns, we're going to have a different number of valence electrons. And if you remember, these transition metals can get weird about exactly what number is on those atoms. So for this video, we're just going to focus on these simpler atoms that are at the top of the periodic table. So let's start with carbon. So carbon is sitting right here, just counting from 1, 2, 3, 4. In that column, it has 4 valence electrons. So for its Lewis structure, all we have to do is draw 4 dots all around the carbon. So boron is 1 to the left, so it's only got 3 valence electrons. So we can just go dot, dot, dot. And we can keep doing this for all these different atoms. Lithium, beryllium, which have 1 and 2 electrons. So nitrogen, just counting up, has 5 electrons. And we can see in this case, we've put both of these electrons in a pair because we can't spread them out equally. Going on to oxygen, it's got 6 electrons, making 2 electron pairs when we're equally distributing them around the atom. Fluorine, which has 7, leaving 3 electron pairs, and then ending up with neon with 4 electron pairs or 8 electrons. And we can complete this a little more. Let's go above to helium and hydrogen, which is just above lithium. Now, these are special because this is the row that only has 2 atoms. So instead of going from 1 to 8, we just go from 1 electron on hydrogen and 2 electrons in a pair on helium. So these are the basic atoms we can look at with Lewis structures. And we can see, again, on this second row, we go 1, 2, 3, 4, 5, 6, 7, 8, known as the octet rule. So in short, most of these atoms want 8 electrons. Now to quickly show which of these they are, you can think of what's typically in an organic molecule, and we can circle that for carbon, nitrogen, oxygen, and fluorine, all of these kind of middle atoms in this row, those will all follow the octet rule. But on the other hand, we have atoms, for instance, hydrogen wants 2 electrons. Boron, it can have 8, but typically it could have 6. Phosphorus, which is a row down, that could have 10 electrons, and sulfur, sometimes you can even see with 12 electrons. So let's take a look at how we can draw Lewis structures for molecules. So for individual atoms, we can look at just putting dots for every electron. But in molecules, we have bonds holding them together. So a single bond is shown as a line, and that is the same as 2 electrons. As a reminder, that is a covalent bond, where the electrons are shared instead of an ionic bond, where you have 2 ions that are held together. So let's just look at a really basic example of hydrogen gas. So H2 has 2 H's. So we could draw each of those. An H with 1 electron, and then an H with another electron. And we can see that in order to form a bond between those, that'll take up both of these electrons. So we can simply do H line H. So there's our Lewis structure for H2. We can go on to something like oxygen gas, which is O2. Now here we have to do oxygen with its 6 electrons, with its 2 pairs, 2 electrons. Now, we can do this a couple different ways. We can mess around with it and just try and make the octet rule work, because remember, oxygen is one of these atoms that's definitely going to follow the octet rule. Or what we can do is go ahead and count all of these electrons and figure out how many of them we'll need to have in bonds and what we need to have just in their own electron pairs. So here's just all of the math written out where we subtract 16 electrons, which is 2 times the octet of 8, and then we can subtract those 12 electrons and then divide that by 2 to get 2 bonds. And you can do all that math, or you can kind of just look at these molecules and start forming bonds. So for instance, you could go and just do an O line O, draw out your atoms, and then the electrons around them. So 1, 2, 3, 4, 5, 6 electrons on this oxygen. Then 1, 2, 3, 4, 5, 6 on this oxygen. And we can see here 7 electrons shared within one of these oxygens, which does not follow the octet rule. So we can go ahead and continue this by just doing oxygen double line for a double bond, fill in the other 4 electrons in each, and now we can see we have 1, 2, 3, 4, 5, 6, 7, 8 electrons on each of these oxygens. So there's kind of 2 different ways to do it. It's really your preference, whether you want to do a little bit of math to get an answer, or if you want to just kind of mess around, and with time you can memorize a lot of these simple molecules. So let's continue on with just a couple more examples. C2H6. So like any other hydrocarbon, we kind of have the carbons in the middle, just like that. And now we can go ahead and put down our electrons. So each carbon has 4 electrons, and each hydrogen only has 1 electron. So let's just go ahead and make sure we're following the octet rule. So with this carbon, 1, 2, 3, 4, 5, 6, 7, 8. Yep, carbon's fine. Then the other carbon's just the same, it's symmetrical. And then each of these hydrogens, remember, don't follow the octet rule, but they do follow the, what you might call duet rule, because hydrogens and heliums want 2 electrons in their valence shell. So since this all checks out, we can just draw it out with lines for all these bonds. So there is the Lewis structure for ethane. So now let's change it up a little different. So instead of 2 carbons and 6 hydrogens, we'll have 2 carbons and 2 hydrogens, known as acetylene. We have a couple carbons, and now let's just put our hydrogens next to these. So we can draw all these valence electrons, 1, 2, 3, 4, 1, 2, 3, 4, and 1 on each of these hydrogens. And so now, if we try and do just these hydrogen-carbon bonds, these carbons still aren't satisfied. They only have 1, 2, 3, 4, 5 electrons. So we can kind of sketch it out over here and then draw it more cleanly. We can do 1 bond here, which will make it 1, 2, 3, 4, 5, 6 electrons. Well, that helped us, so let's add another bond. Let's see, that added on 1 more shared electron, so that's 7. So if we squeeze 1 more bond in there, that will result in 1, 2, 3, 4, 5, 6, 7, 8 electrons for each of these carbons. So if we actually draw out the true Lewis structure, so hydrogen on one end, these 2 carbons, the other side with another hydrogen, the key thing is that we had to form a triple bond in order to complete the octet rule. So now that we've gone through the first step of our roadmap, looking at Lewis structure, we can turn our attention real quick to electron pairs. So this is pretty much a secret tool that will help us later. So on some of these molecules that we just saw, so like in ethane, we have carbons and hydrogens. And in this molecule, all of these electron pairs are in these bonds. So those are all bonding pairs. Now in something like water, for instance, water's Lewis structure looks like this: an oxygen, 2 hydrogens, and then 2 more electron pairs on the oxygen. So in this case, we have 2 bonding pairs and 2 non-bonding electron pairs. So as simple as this seems, just looking at whether it's in a bond or pairs on an atom, this is going to be really important when we look at the actual geometry of these molecules. And real quickly, you might see in some other classes, you can look at the actual orbitals of these. So you can look at how there's, what you can call p orbitals, and then there's s orbitals, which are like figure 8s and circles, and those interact to form bonds. If you look at this, it gives you a better understanding of why bonds act in certain ways, and especially looking at say how much energy it takes to form or break bonds. So now that we've looked at electron pairs, we can go ahead and focus on the geometry of molecules using what's called VSEPR theory. Now, what is VSEPR? Are we talking about, those little Italian scooters? No, we're talking about VSEPR, which stands for valence shell electron pair repulsion. So those are a lot of words that mean a lot of things, but in essence, electrons don't like being together. You put some electron pairs together in that valence shell, and they're going to repel against one another and try and spread out. So if I was going to rename VSEPR theory, I would call it electrons spread out theory. That's pretty much all it is. So within VSEPR theory, we can look at the specific geometries of molecules that having different numbers of electron pairs will cause. So say we just start making a table where you have the number of electron pairs, what we call this type of geometry, the angle that's usually formed, an actual diagram. So say we have 2 electron pairs. This is known as a linear molecule, and just like any other line, we have an angle of 180 degrees. So seeing what that actually looks like, we've got a couple of non-bonding electron pairs on the end of a molecule, and then inside it, we've got 2 bonding electron pairs on a single middle atom. So this whole thing is going to have an angle of 180 degrees. A quick example of that would be something like carbon dioxide. It's got a couple of double bonds, electron pairs on those outside oxygens, but in essence, it's just spreading out as much as possible because we've got 2 sets of electron pairs. Say we bump it up to 3 electron pairs. Now this is going to be called trigonal planar. We've got an angle of 120 degrees. So this looks like a central atom, 3 different bonding electron pairs, or non-bonding electron pairs, in this case 120 degrees. And then 4 different electron pairs. Tetrahedral, we've got a central atom, 4 different non-bonding electron pairs around it. So we've got 1 at the top, and imagine this like any other pyramid, 3 different pairs at the bottom, 4 different bonding pairs, and to kind of complete the picture, let's just draw some lines here to think of this as a triangular pyramid. So that was the basics of VSEPR theory and looking at the geometry of molecules. Now let's look specifically at some more of those bond angles. So again, let's just focus at having 2, 3, and 4 electron pairs. Another term you can, by the way, call an electron pair, because an electron pair might refer to bonding or non-bonding. You can also call this an electron domain. So we're basically just saying, hey, there's some electrons that are sticking together either in a bond or in a pair on an atom, so that's called a domain. So starting with 2 electron pairs where we saw some linear molecules, once again, all of those will just have 180 degrees. Is the simplest one because all we can do is spread it out as long as possible. So one example I gave was with carbon dioxide. Another example could be something like hydrogen cyanide. In this case, we have a single bond and a triple bond on this carbon, and a couple more electrons down here. But once again, this is 180 degrees because it's linear. So now let's go back again to 3 electron pairs, or trigonal planar. So something like boron with 3 fluorines on it. These angles are all going to be 120 degrees. But there's another form of having 3 different electron domains, and that's known as a bent molecule. And no, we're not referring to the famous bent of tau beta pi. We're referring to something like ozone. So ozone is O3. Just looking at the fact that this molecule has a central atom, but only 2 atoms outside of the central atom. 2 electron domains with these outside electrons. We've also got this electron domain on top of it. So you can look up like the actual bond angle of ozone, but if we just say in general for a bent molecule, this angle is going to be something less than 120 degrees. And again, thinking about VSEPR theory, as I like to call it, electrons like to spread out theory, electron pairs are going to repulse these atoms further away from it, so this angle will be smaller and smaller. So here are these 3 different forms we can do for 4 electron domains, or they're called tetrahedral, trigonal, pyramidal, and once again bent. And so similar to 3 different electron domains, we have a certain value, 109.5, if we have all those atoms around it. we will have an angle less than that, so less than 109.5, if we have a single electron pair. And then if we have, again, what's known as bent with a couple different electron pairs, it's again going to be something imprecise, something less than 109.5. So you can look at, again, 5 and 6 and so on electron domains. Those are the basic ones that we'll show in this video. All right, now that we've looked specifically at different bond angles, let's look at how that can come together to look at the polarity of a molecule. So the polarity of a molecule is basically saying, is there a difference in electronegativity or a difference in kind of the density of where the electrons end up? So a classic example, hydrogen chloride or HCl, based on the Lewis structure, or you can think about the fact that chlorine is more electronegative. But what we can do is label this as a delta minus for more electronegative, and this is a delta plus for more electropositive. You can draw this arrow with a line towards the electropositive side, and this arrow is pointing towards the more electronegative side. And because there is an arrow pointing, this is going to be a polar molecule. If we look at something more complicated like water, we have oxygen and a couple hydrogens. Those electronegativity vectors are both going to point towards that oxygen. We could say, oh, we've got two vectors pointing in one direction. It's kind of like winds in two different directions, and so we have kind of a net vector in one direction. But all we really care about is the fact that there is an arrow, so this is again going to be polar. Now if we look at CCl4, which if we drew out has a carbon in the middle, and then it's this pyramidal form with all these chlorines. These chlorines are pulling out that electron density in all these directions. So you say, oh, we've got all these arrows, it must be a polar molecule. The thing is, each of these arrows is exactly counteracting the other one. Since you've got pressure in all these directions, you don't have a single direction. So this is actually a non-polar molecule. And then you could have some other non-polar molecules that are basically just not even having electronegativity difference. So now we've looked at polarity, and we've gone through our entire roadmap of understanding how we can look at the actual shape of a molecule. Let's look at a full example where we'll go through every one of these steps. Ammonia. We can write out its molecular formula, NH3. So let's start with Lewis structure. So we can put nitrogen in the middle. It will want to obey the octet rule, so it makes sense that it's going to want to form some other bonds. So we'll just spread out these hydrogens. Each hydrogen has one valence electron. Then nitrogen, because it's 1 to the right of carbon, has 5 different valence electrons. So right away we can see the fact that we can form these carbon-nitrogen bonds, but we're left with an electron pair on the other side of it. So we'll clean this up a little bit. So now let's identify that once again. 3 different bonding electron pairs, and then 1 non-bonding electron pair. So counting all of these, we've got 1 non-bonding pair and 3 bonding pairs. So let's go back to our VSEPR theory and say 4 different electron pairs. That's going to be some form of tetrahedral. So we can sketch this out as having nitrogen in the middle, hydrogen, 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 and at the top we're going to have this electron pair. More specifically, we can kind of draw it as an electron cloud on top to show that that's similar to a bond in its weight of how much we're considering it. So that's the VSEPR theory side of it. Now if we look at specifically the bond angles, it's not going to be tetrahedral because we don't have all of those atoms attached. So instead it's going to be trigonal pyramidal with 1 electron pair. So from that, we know that it is a bond less than 109.5 degrees. So those two together, we've got that bond angle, trigonal pyramidal. And then finally, let's look at the actual polarity of ammonia. So we know that nitrogen is going to have a delta minus on it, while all these are going to be delta plus. And then all of these atoms, again, we point the arrow towards the negative and kind of put the line here to make positive. So we can see, it's kind of hard to picture it, but if we think of the 3D shape, all of these are going to be pointing to the nitrogen, and then these electrons are actually going to pull density out of the nitrogen in the middle and push it up. So we kind of have this total vector going up, making this a polar. So once again, we're able to look at the Lewis structure of it, and then from that, see how the electron pairs are bonding and non-bonding. We saw how the geometry of the molecule is predicted by VSEPR theory. And then we could specifically look at what sort of bond angle we would see. And then finally, we saw if it was polar or non-polar. So those are the basics of what you can do to predict the shape of a molecule.